Welcome! Today we will be learning about judgments, judgment forms, inference rules, and derivations.
I'm Ivona.
I'm Casey.
I'm Matt Daisley.
And I'm Tyler. Judgments. A judgment is a statement about a set of objects. It asserts a relation between that set of objects. In the example below, you can see E1 evaluates to E1 prime, which is the relation that has been set between the two objects E1 and E1 prime. A judgment form is the relation itself. Also in the example below, you can see another judgment. E1 plus E2 evaluates to E1 prime plus E2. These judgments both have special names, but you'll learn about them later, so stay tuned. Judgments are used throughout all programming languages. This includes both imperative and functional languages. Let's get started. Judgment form E:(T). This translates to expression E is of type T. The relation has the parameters E and T, as well as the punctuation colon, which is an arbitrary symbol chosen to represent the relationship between E and T. For example, num variable :int, as I'm sure you guys are all catching on. This translates to num variable is of type int.
What we need now is a way to understand the relation between a set of objects that is a judgment form. To do this, we have inference rules, which give us a way of inductively defining judgment forms using premises and conclusions. On the slide you can see the structure of a simple inference rule. Notice here we use J as a meta variable to represent a judgment. On the top of the line is the premise, which are 0 or more judgments that we use to justify the conclusion below the line. If we can show the premises are true, then the conclusion is also true. In other words, the premises are sufficient to derive the conclusion. We will talk about derivations in a minute. You can also see on the slide that it is possible to have an inference rule with no premise. We call this an axiom. This is just a statement that we assume to be true, which serves as a starting point for inferring any other truths. Let's see an example that you may recognize from the PDF. Here we are defining the language of natural numbers using judgments and inference rules. We start out by defining nat as a set of syntactic objects that describe the natural numbers. With that, we can say the syntactic object n is a natural number in the set nat.
We can define the natural set using just these two inference rules. The zero rule provides the conclusion that 0 exists in the natural set. This value existing in the natural set is given to us, so the inference rule takes the form of an axiom, meaning no premise is needed to reach the conclusion, and 0 exists in that is the only judgment in the inference rule. The successor rule is used to provide the rest of the natural set of numbers. Using the premise that a number n is in the natural set, we can conclude that the successor of n, s of n, is also in the natural set. Two judgments in this inference rule are n exists in nat and s of n exists in nat. Since the set of natural numbers are all the integers starting from 0 and going to positive infinity, we can reach any given number by beginning at 0 and then continually taking the successor until we reach the goal value. A judgment is said to hold if we can demonstrate it using inference rules to compose applications. This is known as a derivation. A derivation can be thought of as a tree where any node in the tree is an application of an inference rule. The root would be a particular example, and each subsequent child is a derivation of a rule's premise. This continues until a leaf is reached, where the leaf are axioms. Derivations are also commonly used for creating parse trees, in particular for checking ambiguity in grammar by breaking down sentences into the components that derived them.
Let us attempt to do derivations on inference rules and axioms. For example, we will demonstrate and prove that s of 0 exists in the natural number set. First, we start at the 0 axiom, which self-evidently concludes that 0 exists in the natural number set. From there, we can derive from the axiom to the successor, where the premise that 0 exists in the nat set leads us to the conclusion that s of 0 also exists in the natural number set. If we continue in our derivations, we can go into the next successor, which holds in the premise that s of 0 exists in that. From there, we can conclude that s of 0 also exists in that, thus showing that s of 0 existing in the natural number set holds. If we wish to continue, we could repeatedly use derivations on these inference rules and axioms to show that some constructed function s can be used inductively to reach any nat. Here are more examples of inference rules and judgments. The first example is a basic inference rule where the premise shows mathematically that n prime equals negative n. In the conclusion, we would use Scala to show that negative n evaluates to n prime. In the next example, we use two numbers as opposed to one, where the mathematical premise holds that n prime equals n1 plus n2, and the conclusion holds that n1 plus n2 evaluates to some n prime. In the third one, we see a combination of booleans and numbers in the inference rule, where the premise holds that b prime equals n1 less than n2, and the conclusion holds that n1 less than n2 will evaluate to b prime. Lastly, we have a Boolean axiom, where the conclusion holds that false and e2 will evaluate to false, which is an example of short-circuiting, which you may find in another student group's video.
To demonstrate the topics we have discussed, let's take a look at an example from Homework 4. This page of inference rules defines din-smala, a miniature dynamic programming language that we implemented in Scala for the assignment.
Let's take a look at the binary operator inference rule. This is one of the rules that defines the evaluation order of expressions that use binary operators. This rule concludes that when you have an expression in the form of a number n, a binary operator Bob, and then an expression e2, the next step taken is to evaluate the expression e2 to e prime, as seen here.
To reach this conclusion, we define the premises above the line. We begin with a judgment that says expression e2 evaluates to e2 prime. The next judgment says there exists a binary operator Bob in the set plus, minus, times, and less than.
Let's look at a concrete example. Say we have 5 plus the expression 3 plus 2. This would evaluate to 5 plus 5. Given the premise that the expression 3 plus 2 evaluates to 5, and that the addition symbol plus exists in the set of binary operators.
Thank you for watching. We hope you enjoyed the video and learning about derivations, inference rules, judgments, and judgment forms. If you have any questions or comments, please feel free to leave them in the comment section below or email one of us at the following addresses. Thank you.